This is a tutorial on number sets and the counting principle. The first thing that we're going to talk about in this tutorial are number sets. And to illustrate a number set, we're going to use a set of 3 marbles. We have 1 green marble, 1 blue marble, and 1 red marble. Now there's lots of different subsets that we can get from these 3 different choice of marbles. These subsets all have 0, 1, 2, or 3 elements in them, and an element is just a selection, so it would be a marble. If I wanted a 0 element subset, well, I would be choosing 0 marbles out of the 3, and there's only one way to do that. I don't choose any marbles. If I wanted a 1 element subset, that would mean I would choose 1 marble out of the 3 possible. And there are 3 different subsets for choosing 1 marble. I might choose the green marble, or I might choose the blue marble, or I might choose the red one. So there are 3 different 1 element subsets from these 3 different marbles. Just like there's only one way to choose 0 marbles. Now if I wanted to choose 2 marbles or 2 elements out of the 3 possible, well, I might choose a green one and then a blue one, or I might choose a green one and a red one, or I might choose a blue one and a red one. Those are the only 3 ways I can choose 2 out of the 3 marbles. So there are 3 different ways to create a 2-element subset from this set of 3 marbles. Now if I want a 3-element subset, that means I'm going to choose every one of the marbles. I would have a green, a blue, and then a red one. So there is only one way to choose a 3-element subset out of 3 different elements. If we add up all of this, 1 plus 3 is 4, 3 plus 1 is 4, 4 and 4 would give us 8. So there are 8 different element subsets for the choice of 3 marbles. If you have a set, say it's set A, and set A has n elements in it, then set A has 2 to the n possible subsets. So the fact that we had 3 different elements in our set of 3 marbles, we ended up with 2 to the 3rd power subsets of our 3 elements, which was equal to 8. So here we're asked to determine all of the possible subsets of this number set that's just listed as A, B, C, and D. Well, there are 4 elements to this set, which means we should get 2 to the 4th power amount of subsets. 2 to the 4th power is 16, so we should get 16 different possible subsets of A, B, C, and D. First, we'll have some 0 element subsets. And there's only one way to do that. Don't choose any of the possible. Then we might have a 1 element subset. And how many different ways can we choose 1 item out of the 4 possible? Well, we might choose A, we might choose B, we might choose C, or we might choose D. So there are 4 different ways to do that. We might have some 2 element subsets. Then we would choose A and B, or maybe A and C, or maybe A and D. We also might choose B and C, or B and D, or we might choose C and D. So there are 6 different possible 2-element subsets. Now 3-element subsets. We might choose A, B, and C. We might choose A, C, and D. We might choose A, B, and D. Or we might choose B, C, and D. So there are 4 possible 3-element subsets from this set of A, B, C, and D. We have 4 elements, so there's one more to do. A 4-element subset. Well, there's only one way to do that. We just choose every one, A, B, C, and D. Now let's check our work. There's only one way to choose 0 elements. You just don't choose any. There's 4 ways to choose 1 element. There are 6 different ways to choose 2 elements, 4 different ways to choose 3 elements, and 1 different way to choose all 4. Add this all up, and it comes to 16. So we did find all of our possible subsets, and they're all listed right here. Now there are many different ways to illustrate number sets. Here we're told that there are 52 cards in a standard deck, and we want to know how many of these cards are hearts, how many of these cards are face cards, and how many of the cards are both a heart and a face card. Well, a popular way to illustrate a number set is to use a Venn diagram. This is a Venn diagram. This box and all the dots in it represent each possible card that we might choose out of the deck. Inside this circle, there are 13 red or purple dots. These 13 dots represent the amount of hearts that are in the standard deck. The blue dots represent the amount of face cards that are in the standard deck. These purple dots, they represent the cards that are both hearts and face cards. And then all these black dots are just cards that are neither a heart or a face card. Now there are 13 hearts, and every point inside this circle here is a heart. There are 12 face cards, and every point inside this circle is a face card. Now you'll notice that these 3 points in the center are actually in both circles. That's why those are the cards that are hearts and face cards, because they're in the heart circle and they're in the face card circle. So this is how we use a Venn diagram to illustrate how many of the cards are face cards, or how many of the cards that are hearts, and how many of the cards are both. We just create these circles to group the individual possible numbers or sets together. Another way to think of this is a 52 different numbered set. The hearts are a subset, the face cards are a different subset, and the combined hearts and face cards are a different subset. Now we're asked how many of the cards are hearts. Well, we can count the dots, or if you just know, there are 13 hearts. How many of the cards are face cards? Well, we know that too. There are 12, and you can count the dots that are inside the face card circle. And then how many of the cards are both? Well, the 3 that are in the joining of the 2 circles illustrate the 3 cards that are both hearts and face cards. But what if we wanted to know how many cards are hearts or face cards? Well, then we could count the dots. We could do 13 plus 12. That would get us 25. But that's not actually the amount of cards that are either heart or a face card, because what we've done is count these 3 points in the center here twice. We counted them when we counted our 13 hearts, and then we counted them again when we counted our 12 face cards. So we have to subtract 3 from this total because we got to take off the 3 that we counted twice. So really there are 22 different cards that are either a heart or a face card. Now there's another way to illustrate this addition and subtraction that we just did. This first term here, this is the number, and then this A with this crazy U and a B, this means the union of A and B. This means anything that is A or B. Or you can think of a heart or a face card. So this would be the number of hearts. This would be the number of face cards. And then this number of A, and this is called the intersection of B. But you can think of this as A and B if you want. This is the number of cards that would be hearts and face cards at the same time. So if we wanted to know the number of cards that are a heart or a face card, well then we would add up the number of hearts, which is 13. We would add that to the number of face cards, well there's 12 of those, and then we would subtract the number of cards that are both hearts and face cards. Well, there are 3 of those. This brings us back to our 22. So the number A union B would be 22, or the number of hearts or face cards would be 22. This is a popular way to write our formula. So recognize what this union and this intersection and the difference of what these two things mean. One is or and one is and. Now frequently we'll be given different elements of this formula and asked to solve for the missing one. So if the number in the union of A and B is equal to the number of A plus the number from B minus the number from the intersection of A and B, well, if we're told that the union is 20, this should be equal to the number A, which we're also given, and the number B, which we're also given. And we want to find the number A intersection B. Well, we have 20, and that's equal to 12 plus 14, so that's 26. And then we're going to subtract the intersection of A and B. If we rearrange this, we'll find that the number of elements in the intersection of these two sets, A and B, well, that's equal to 6. Now you may be given any different number or every different element of this equation, but usually it's just an addition and you just have to solve for the missing part. In this case, we solved for the intersection, and that was equal to 6. Sometimes we'll be given a Venn diagram illustrating the number of different elements in each different set. We have set A, B, and C in this Venn diagram, and these numbers illustrate the amount of elements in each set. So there are 9 elements not in any of the 3 sets. There are 14 elements just in set A. There are 3 elements here that are in set A, B, and C. So we're asked how many are in set A. Well, there are the 14 that are in set A, but there are also 7 that are in set A and B. Well, these are still in set A. So we'll add them to the other 14. There's also these 2 here that are in both sets A and C, but they're still in set A, so we can add the 2 to there. And then we also have the 3 here that are in set A, B, and C. So we can add the 3 to that because those are also in set A. So 14 plus 7 plus 2 plus 3, that's 26. So apparently there are 26 elements in set A. Now we want to know how many are in set A or B, but not in set C. So sets A or B, well, these 14 are in A, these 11 are in B, We have these 7 here that are in A and B. We have these 2 that are in A and C, but our elements cannot be in C, so we ignore those. We have the 4 here that are in B and C, but they can't be in C, so we ignore those. And then we have these 3 here that are in A, B, and C, but since these are in C as well as in A and B, we cannot use those either. So how many elements are in set A or B, but not in set C? Well, 14 plus 11 plus 7. So there are 32 different elements in set A or B, but not in set C. Now lastly, we're asked how many are in sets B and C, but not in A. So for a set to be valid, it has to be in both B and C, but not in A. So let's find all of the possible elements that are in both B and C. That would be all of these elements. 3 of these elements, though, are also in set A, and we've decided to exclude them, but not in A. So these don't count. So how many are in sets B and C? Well, 4 different elements are in both B and C, but not in A. So that's how you use a Venn diagram to determine how many elements are in the different sets. Now the last thing we have to talk about is the fundamental counting principle. And let's look at this example situation. Here Dana wants to buy a new car. She's trying to choose between a Chevy, a Ford, a Mazda, or a Honda. Each vehicle can come in one of 6 different colors: black, green, blue, red, silver, or brown. So how many different combinations of vehicle and color does Dana have to choose from? Well, here's Dana. And she can choose between a Chevy, Ford, Mazda, or a Honda. So she has 4 different choices. She can choose a Chevy, a Ford, a Mazda, or a Honda. Once she's chosen between the 4 different makes of car, she has 6 different colors to choose from. If she chooses the Chevy, she can get a black Chevy, she can get a green one, a blue one, a red one, a silver one, or a brown one. And she has the same 6 choices if she chooses the Ford. Black, green, blue, red, silver, and brown. And if she chooses the Mazda, she can get a black one, a green one, a blue one, a red one, a silver one, or a brown one. And if she chooses the Honda, she can get a black one, a green one, a blue one, a red one, a silver one, and a brown one. Now if we count up all of these different options, there are 6 here, 6 there, 6 there, and 6 here. So there are 24 different possible combinations of vehicle and color that Dana has to choose from. First, she had to choose between 4 different makes of car, and then she had to choose from 6 different colors of those cars. Multiply 4 and 6 and you get your 24. This is the fundamental counting principle. The fundamental counting principle basically states if an event can occur in P different ways, the event would be Dana choosing the type of car, which occurred in 4 different ways. And a second event can occur in Q different ways. You can think of this second event as choosing the color, and that can occur in Q different ways. Well, there were 6 different colors to choose from. Then the amount of different ways that both events can occur is P times Q. 4 times 6 is 24. Now, if there are more than 2 events going on, then you just keep multiplying the different ways that each one can occur. So if there are 3 events and the third one can occur in R different ways, say R was 7, then the 3 events can occur in 4 times 6 times 7 different ways. And that would be 168 different ways of choosing between the 3 possible events or the 3 possible choices. So let's look at an example. Here Joe is making a sandwich. He can choose between white or wheat bread, bologna, ham, or roast beef, and American Swiss or pepper jack cheeses. How many different types of sandwiches can Joe make? Well, we have Joe, and he's going to make a sandwich. His first choice is to choose between white or wheat bread. So there are 2 different choices on the bread. There are 3 different choices of meat, bologna, ham, or roast beef. So after we choose what type of bread, we have 3 different choices between the bologna, ham, or roast beef. And then lastly, we have 3 different choices of cheese to put on the sandwich, American Swiss or pepper jack. So since we have 3 different choices, we multiply this by 3. So how many different types of sandwiches can Joe make? Well, he can make 2 times 3 times 3 different types. 2 times 3 is 6, times 3 again is 18. So that's how you use the fundamental counting principle. And now that we've learned how to do that, that completes the tutorial on number sets and the counting principle.